Thank you very much. Quick disclaimer, as you might be hearing, I'm losing my voice, so I have tea here to support me. Hopefully my voice will last until the end of the talk. But thank you very much for the intro, Jan. And yes, today we're going to talk about multimodal RAG systems, and I'll be using vLLM and I'll be using Pixtral for Mistral. Quickly, as an agenda, so I will talk and intro a tiny bit about vector search, vector databases, so that you have a better idea of how everything works behind the scene. There's a lot of talk by the tech databases. There's lots of people saying like, oh, mine is better, mine is better, mine is doing that. I'm just going to give you a quick idea of, what to look for and which index to pick and when. Then, in my opinion, we don't talk enough about embedding models. So I will talk about those. You will then see me also talk about actually vLLMs, Pixtral, how VLM models are working, and then at the end I have a live demo which hopefully should work. But yes, as I was introduced, I'm Stephen Batifol. I was up until last week a developer advocate for Milvus, which is an open source vector database, and now I'm joining Black Forest Labs, which is an image generation company. So if you have questions about that, you can also talk to me later on. But quickly, what is vector search? For the past 2 years, vector databases have been like, oh my God, you need to use that. But a lot of people actually don't really have an idea of what it is and how it works. So quickly, we're going to go through that. And why is it so popular? Why is it everywhere? And why it's still important nowadays? It's because vectors unlock your unstructured data. So think of images, audio, videos, the user documents. Then what's happening is that you're going to put that through your deep learning model, and then that's how you get vector embeddings. You then store them in a vector database, and then from now on you can perform search. So you can perform RAG, Retrieval-Augmented Generation, but you can also perform other things. A lot of people are talking about RAG. For the past 2 years we've been talking about RAG, but there are other things. There's drug discovery. A friend of mine, he's a CTO at an AI protein company, and they create proteins using AI, and then they search through the protein using vector search. So this is also the kind of thing that you can unlock. Also very good for recommendation system and anomaly detection. And quickly, how it works is that, okay, you're going to transform the unstructured data, and then you project everything into a vector space. Here, for the demo, it's only in 3 dimensions. The blue points you see here are vectors. And you have to imagine that you're trying to make things that are semantically similar. You're going to try to make them close together. So here you see on the image, you have the image of a banana, and then you have the text banana. Those two are close because they are semantically similar. Same for the cat, for the text of the cat, and then the image of the cat. And those two, like the pets, basically, with cat, dogs. Then you can also see that they are very far from the different fruits. And this is why we project everything into a vector space. Obviously, we don't work in 3 dimensions. Most of the embedding models are more in the thousands, 2,000, 3,000, and we'll see that later on. And how do you make sure then, how do you find the points that are very close to you? This is, actually we're just going to compute nearest neighbors. So you can brute force it. This is actually a real thing. You have an index that I will talk about later on, which is called flat, which is actually brute forcing that. And you're computing all the points, you're computing all the vectors to find the one that is the closest to you. But the problem with this one, it doesn't scale, obviously. It is amazing up until you have hundreds of thousands of vectors. When you arrive in the millions, it's not going to work. If you're in the billions, don't even think about it. And so what we do is then we're going to approximate nearest neighbors. So we're using machine learning models that have been trained actually to predict how to approximate close neighbors. And this is what we're calling indexes. Indexes, it's a bit of a fancy word, or I find it fancy. Well, I find it very complex, very opaque, but actually behind the scene, it's just a machine learning model. And then you have different trade-offs. So you have to take into account model complexity, the quality, and the search speed. And those 3, they're close together. They're always intricate. So if you want to have a higher search speed, you will have to lower down the model quality and also lower down the model complexity. Maybe actually you want to have a better model, then you will likely have to trade off. With the search speed, it will be lower, and the model quality also has to be lower down. And same if you want to have a model of better quality, then the search speed will be lower, but also the building time will also be lower. This is what we refer to for like the index building time. This is usually what is very important. And in the end, I'm going to insist just to make sure that you can follow on 3 different indexes, because I work for a vector database, so like I work with indexes every day, but it might not be clear to everyone. So flat, this is the one we call, this is for the brute force. You have a query vector, and then you're literally computing the distance to all the vectors that you have in the vector space. This is nice. When you have small scale, actually works. But then when you have more data, usually you go for IVF, which is inverted file index. This one, instead of actually computing all the vectors, you're going to create centroids, and then you're going to compute the distance to those centroids, and then once you find the closest one, then you're going to compute the distance to all the vectors within this centroid. For this one, you have to tune, you have different parameters that you have to take into account. For example, how many centroids are you going to have a look at? So this one requires a bit more tuning, but actually if you tune it well, it can have very, very good performances. And last but not least, HNSW. The name is very hard to pronounce. It's Hierarchical Navigable Small World Graphs. This is one of the most popular ones. This is the one that is always used by vector database by default. And this one, it's a graph-based index, meaning that it's very performant, but also to build it, it's going to take actually quite a long time. You know, this is the one where if you want to update your index very often, then you likely don't want this one because you have to rebuild the graph all the time. And how it works is that you have an entry point, and then you're going to try to find the nearest neighbors. And what happens is that, you know, the graphs are divided into different levels. And at the first level, you have only a couple of vectors. Then you're going to find the closest one to you. And once you do that, then you're going to go a layer down. Then there you have a bit more vectors. And then again, you're going to try to find the closest one, and again and again. And you go so down 2 different layers. And at the end, you arrive at the last layer where you have all the vectors, and then that's how you found the nearest neighbors. So there's actually lots of indexes. I just talked about 3, but here we can see we have like GPU index based, which is the one on the top left. You can see the text is a tiny bit small, but you have to trust me. But the one on the top left, it's GPU index, so you have to imagine the latency is very, very good. It's very low. The throughput is also very high. The index speed, the time to build the index, is actually very low, but it's way more costly than if you were to use, you know, RAM-based index. HNSW, I just mentioned it. It's like a good middle ground, I would say. And then you have other ones like DiskKNN, which is a disk-based index. So this one, very cost efficient. We're very happy here. Also actually has a very good accuracy, but the latency is going to be higher, and the time to build the index is also way much higher. So it's like all about the balance and all about what you want. You know, there's not one that will fit for everything. So as a summary, so you can like leave this talk and have a better idea about indexing. So flat, very simple, very accurate. Actually, if you want 100% recall, this is the only one that is able to do that, but it's slow at scale. IVF, fast enough actually for most tasks. I believe that a lot of people should use IVF, but you need tuning, and the accuracy can vary. HNSW is the classic one, very high query per second, great accuracy, but it is slow to build, and it's costly to update. And finally, the one I mentioned as well that is running on disk, DiskKNN. This one will allow you to scale beyond your RAM, because you will actually build the graph directly on disk. And the problem with that, though, is that obviously you have a higher latency. So everything is a trade-off. Have a look at, you know, what you want, what you need for your company. And then I mentioned embedding models. They are, in my opinion, one of the most important pieces that you can think of, and I don't think people talk about them enough. We talked a lot about LLMs. We talk a lot, you know, about foundational models, but never about those small embedding models. So yes, it is extremely important to choose the right one, because you may have the best LLM, you may have the best vector database, you may have the best agentic system, If you don't have good embeddings, you will likely never reach the full potential of your RAG system. And then you may ask, oh, how do you find the best one then for you? This is from Hugging Face. They have a leaderboard directly about embedding models. You can see, you have a rank. And I want you to forget this rank, because this is not the way you should look at the leaderboard. Because by default, you may go and be like, okay, here at the moment, Gemini is actually the first one. You may go and be like, okay, I'm going to use Gemini. They are obviously first ranking. This is the best model for me. But that's not the way you should approach it, in my opinion. First, you should have a look at the embedding dimensions. So this is the third column that you see, where you see like Gemini is 3072. This is the dimension that I've shown at the beginning, where you had 3 dimensions. Now you're projecting things into 3072. And this one is very important because depending on the vector database that you're going to use, it may or may not be able to support it. pgvector, for example, which is an extension from Postgres, they work with paging. And when they work with paging, it means the way for embedding dimensions, they don't support embedding dimensions with more than 2,000. They do if you quantize your embeddings, but that means you're going to have a trade-off in quality. And so those are like the things that you have to look at. If you want to use an embedding model with pgvector, for example, without quantization, you would have to go for the multilingual one, which is 4th in the leaderboard. So have a look at those. But also, that's not it, have a look at the different tasks that you have. So here you see in the leaderboards, we can see classification task, we can see clustering task, instruction retrieval, and then you have way more tasks as well actually behind the scene. So then, now recently actually what's very nice from Hugging Face is that they release different filters. So really, first, find the languages that you want to work with. Are you working, for example, with German and English documents? I'm based in Berlin. So I work actually with a lot of documents that are German and English. I then therefore use embedding models, that have been trained on those 2 languages. Because then, I can either write in German or I can write in English, and then they will understand it. Also, make sure you have the correct task, because maybe you're going to have a retrieval system, but maybe you have a very different task, and then embedding models have been trained on those different tasks as well. Same for the domains. Are you working in the medical industry? Are you working in the legal industry? Those embedding models have also been trained on different type of data. So make sure you select a domain that is actually very good for you. And the modalities. Today, I'm going to talk about multimodal RAG. So I will have to use an embedding model that is supporting images and text. But maybe on yourself, you want to use text only, or you want to use images only. Then you have to find the right one. Finally, do you want to have an open source one, or you don't mind, you can just go through the API. Those are all the filters that you have. And then once you find the right filters, then maybe you will find your best embedding model. Maybe it was ranking, 12th, but it may be way better for you and your use case. And in the end, at the moment lately, all the labs are like pushing to be first on the ranking, but just because you're first doesn't mean that you're the best for your use case. So yes, please use embedding models that have been trained on similar data. And I need to drink tea because my voice is I'm losing my voice. Sorry, I'm back. Okay, so now we have an idea of how vector search is working, which embedding models to use, but then how everything is working together. We've seen this one already. You have your unstructured data, you transform it into vectors, you get the embeddings. You store that in your vector database. And then the new part now is that you have your user coming and they have a query. Maybe they have they're giving you an image, maybe they're giving you some text, but they want to learn something. So again, you're going to transform that into vectors to get the vector embeddings. And this is then where you're going to perform the similarity search that we talked about before. And this is where the index is very important. This is what we're doing now. The index is like finding the closest points. And then once we're happy, we get the results, and then we give you back those results. And this is, what vector databases in general are working on, and they're working to improve. Similarity search, in theory, is very simple. It's very simple when you have like a couple of hundreds of thousands of vectors, But once you reach scale, this is the hard part. How are you going to update your index? How are you going to handle upsets? And how are you going to handle all of the things? And last point about evaluation. I could give an entire talk about evaluation, about how to evaluate RAG. There's a lot of vibe coding lately, but please don't vibe check your RAG. Like, have a proper evaluation, because first, you can't fix what you don't measure. So Jan mentioned, I used to work for MLOps when it was cool. And when I joined my previous company, we had a couple of models running in production, and we had no idea, actually, if they were performing well or not. We had no evaluation. We couldn't check the latency of the models and those things. So then, well, then you have no idea if they're good or not, So same for RAG. If you can't measure it, you can't fix it. Also, very famous person is called Hamel. He's always like, look at your data. Always look at your data. Don't assume that your data is perfect. Test each part and not just the whole pipeline, like test the RAG system, test the embedding models, test the retrieval, test all those parts and not the entire thing only. Use LLM as a judge. This is also very powerful to score answers. And measure retrieval recall as well, and not only the model output. Once you have that, then you have a better evaluation system, and then you will not only have your gut feeling, you will actually have a strategy. And why is it so important? Is that so many companies are training LLMs. Then you have a new one. Like a couple of months ago, Claude was the cool one. Now apparently it's Gemini 2.5, which means if you change your LLM, then you want to make sure that it's actually still very good for your system. And if you don't have an evaluation, then you have no idea. And then you'll be like, okay, I guess it works, but actually you want to be confident. So that's why. Vibe coding is fine, but no vibe checks for evaluation. So summary, pick the right index, choose embeddings carefully, and then evals. And quickly about RAG, no worries, I will not introduce it. I'm certain that everyone here knows what it is. But I have a quick question. Who think RAG is dead? Can you raise your hand if you think it's useless? Okay, a couple of people, cool. Well, maybe, okay. Appreciate you coming. Still, maybe I can convince you otherwise. Llama 4 was released last Saturday, so a couple of days ago now. This is a benchmark that was everywhere yesterday on socials. So yeah, I had to update my slides yesterday. You can see this is about long context. This is to make sure that LLMs actually, they pretend to have long context, but let's see actually when we compare them with different benchmarks. The best one is O1, up until 120,000 tokens for input, we have 53% accuracy, which means you're actually not very accurate. They claim that they have very, very good accuracy at, even millions and millions of tokens as an input, but actually when you train them, you can see that it's still not the case. One, where, I'm gonna give credit where credit is due, Gemini 2.5 Pro, which is making a lot of noise, which is in the middle. You can see that actually very, very good, even up until 120,000 tokens. It actually has a slope at 16. No one knows why. But it would be up until 8, and after 16, it's very good. So I don't know, maybe give them longer prompt, so they reach out, 32,000 or 16K when you use it. The only problem though is that it's going to be quite high. The latency will be quite high. Also the cost is going to be high because 120,000 tokens, it's about 180 to 200 pages long PDF. If you go through an IPO, the PDF is 300 pages long. Just to give you an idea. And Llama 4, which has supposedly an input token of 10 million tokens, we can see it at the bottom, unfortunately. The accuracy for Maverick is 28% at 120,000 tokens, and for Scout, it is 15%. So I imagine we can scale it up. We can go to 10 million, that's fine, but then what matters in the end is the accuracy that you have, and the latency, and the cost. And just want to highlight that because labs are pushing a lot for okay, we have very high input tokens, and that's cool, but if your accuracy is not good, then I don't want to use it. So hopefully, I still convince you that RAG is still here, because RAG in the end is only retrieval plus LLM. And sorry. And the R part of RAG is actually very, very important. You want to make sure how you're going to use metadata filtering, how you're going to make sure that you have full text search and all those things. So how can we make it better then? We can use the best LLM, we can use the best embedding models, but then we've seen on the benchmarks before that actually they're still not very good. So I mentioned it already, retrieval makes or break RAG. If the context is not clear to you, don't expect the model to understand it. This is usually what I talked about with customers. It's like when you get chunks back, if you don't understand those, and you're the one asking the question, then the model will not understand it either. So it's something like, make sure that you understand the context, and if you don't, you have to fix something with your RAG system. Good retrieval means making sure that the retrieval has the right context, making sure you're getting all the relevant documents, but also making sure that you don't have too much noise, because then LLMs, will be very confused, and then they'll be like, okay, this is cool, but they're going to be confused. And even the reasoning model now are getting better at that, where they will actually tell you this part is not relevant. I'm just going to skim through it. It's still make sure that if you have a good retrieval, you will have better performances in the end. Also, similarity search is not magic. So models are not trained on your data. They will not understand internal jargons. They will not understand acronyms. And embedding models also compress information, which means that some details will get lost on the way. This is inevitable. This is how it works. Finally, people still search with keywords. So you may have the best embedding models, the best vector search. If people are searching with keywords because they want a specific product, then you will not be able to find it very likely. So we have something else, which is BM25, which is a very old technology now, which is actually also called full text search or keyword search. And it's a ranking function that is used to estimate the relevance of a document for a given query. It's very great because great baseline, it's fast, it's simple, and it scales. So far you'd be like, oh wow, what's wrong with it? It's also really good with acronyms, really good with internal terms. The only problem though is that it doesn't understand meaning. So it only matching words. So on one hand, you have semantic search, which is very good at understanding meaning. And on the other, you have BM25, which is not good at that, but is really good at understanding acronyms and internal jargons. So you can see where I'm going. We're going to combine those two. And then this is what we call hybrid search. Hybrid search is actually combining those two. It's similarity search plus BM25. And at the beginning, you can see here, you have your documents. They go directly into your vector database, and on the other one, you're computing BM25. Once you have your query, you're actually going to run the query. You're going to try to find the best chunks for your vector database. You get those top K, and you do the same for BM25. You get the top K for BM25, then everything is beautiful. You have, on one hand, BM25 coming, on the other one, vector store. And what's happening now is that you're going to use a fusion algorithm. So this is what usually we call a re-ranker. But they're basically fusioning those two results together. They give that back to the LLM, and then hopefully you have better answers. This is usually actually a very good way of having better results, and it doesn't add much complexity to your system. And then I already mentioned it quickly, but metadata filtering is also extremely important. You're going to have more signal, you're going to have less noise. And what you can do is you can store metadata yourself. You can track the source, the author, when was it last updated. Then you can also add your own ones, the company name, the region, the country. You can add all of those. That way you can really use filters to then narrow down the search scope, and then you're going to improve your precision. And also if you want to have, information that is very fresh, you can also that way filter by recency. So you don't have to go through all the data that have been 5 years old, when actually you only want the last one. So with good metadata, you have better context, and then you get better answers. This is what I want you to go out with. And, I'm just going to give you a quick example of how it can improve the results. Let's say you have a query, which is, what's the refund policy for UK orders? You have two chunks. Sorry. You have two chunks. Without filtering, you have the first one, which is okay, customers have 30 days to request a refund. Second one, refunds are processed within 5 business days. And then, you're okay, you see that. And myself, it's what I was saying before. I actually don't have any idea, I don't understand it. I don't know which one is correct. So don't expect your LLM to know which one is correct. It's not magic. It's not going to be like, oh yeah, this one looks beautiful. So usually it will like pick one of those two, will give you an answer, and then that's what we call hallucination. But if we have region in our metadata, then we can filter it by the UK, and then, for example, you get this one, which is UK orders can be returned within 14 days for a full refund. And now somehow you're like, okay, this actually looks legit. You still have to make sure it's correct, but at least now it's actually about the UK and not about any other country where they talk about refunds. So this is the kind of thing you can do with metadata filtering. There's more. RAG now actually just a component about usually with like agentic systems is just a tool that you have. But what I want you to remember is that even if it's just a tool, you have to make sure it's a great tool. You have to make sure it's optimized. You have to make sure you get really good retrieval. You also have graph RAG, which allows you to like boost your retrieval with a knowledge graph. This one really powerful, but only if you need a knowledge graph, and you're working, for example, with entities or things like that, because it's really going to increase the latency, and then you also have to convert everything into graph language. Okay, now we have a better idea. So now we can try and see how we can like build, a self-hosted multimodal RAG system. And I will only be using open source. And I want you to imagine something that, we're all back at uni, and we just missed our class. We're like a student, and thankfully now, all the classes are recorded. So even if we miss it, it's fine. We can, still catch up. But let's say you're using text-only RAG. Then, okay, what you're going to do is like you're going to have transcription of the audio of the class. But this class was about backpropagation in neural network. This is something that is very visual to learn. Usually, you see the backpropagation yourself. And if you're only going to use text RAG, then you're actually not going to be able to catch up on anything. So you're going to use multimodal RAG with like audio, video, and text. And now somehow you can search through the images, you can search through the audio, and then this is going to be the demo later on that I'm going to show you, where you can actually ask questions about the class, and like then it will find the best image to illustrate this point. And this is what it looks like for the stack. We take a lot of different inputs, thinking of like images, video, text. We put them through multimodal embeddings. We store them in the vector database, and then when we search it, then we have this question that is also going through the multimodal embeddings, vector database, and then we give that back to our LLM with a question plus the context that we just retrieved. This is then sent to Pixtral, so we can also send images directly, and then hopefully we get reliable answers. And the tech stack I'm going to use Milvus for the vector database, vLLM for the inference and serving, Koyab for the infrastructure layer, and Pixtral for the multimodal model. I'm using the open source version, so this is the one that I'm going to self-host, and you're going to see later on, hopefully if it works, you're going to see I'm going to self-host it, and then we'll deploy it. So Koyab, why am I using them? First, they're very easy to use. They have auto-scaling, so if I were to deploy this into production, then I can really like auto-scale it as long as I have money on my bank account. And then I can also scale to 0, so if there's no demand at all, then you can scale to 0, which is nice, and then it's going to like start again if you have new user coming. You can build and deploy almost everything. Think from going from like Comfy UI to vector databases to Postgres to vLLMs and to like a lot of different things. You can deploy them. They support basically everything, and they're distributed globally, so you can really go everywhere and then be happy. Milvus, which I'm going to use, it's part of the Linux Foundation, also open source, and it supports like massive amount of vectors. The biggest it supports, it's the distributed version, which scales up to 100 billion vectors. And then you have like different offerings. I won't go into details, but standalone, which scales up to about 100 million vectors, and Milvus Lite, which is just running on your laptop. And it has a lot of different features. So metadata filtering, I've mentioned it, bulk import, if you want to import a lot of data suddenly, disk-based index, full text search as well, and then GPU vector search. This one, actually, I love when I work with customers on this one. It's very useful. Just you need a lot of money, but apart from that, it's very useful and it's very fast. But yeah, GPU vector search, really, really good. And then Pixtral from Mistral. So this is natively multimodal, very strong performance on multimodal task, and it's very good at instruction following as well. The architecture, I'll go a tiny bit more into details on the next slide, but it's a vision encoder that they actually trained from scratch. When I was talking to some Mistral engineers, they were like, yeah, we were not happy with Clip from OpenAI, so they were like, we're just going to train our own. So that's what they've done. And then the multimodal decoder is based on Mistral Nemo, and then it supports different image sizes and aspect ratios. And the architecture is the following. So you can see here, we have two different images. They both go through the vision encoder. And then what the vision encoder is doing is actually generating tokens for those images. And then you want to flatten all those tokens so that you can put them directly to your decoder. And how you're going to do then, how you're going to know, that this is the end of the first line of the image, is that you're inserting those special tokens here. You can actually see my mouse. You can insert those B, which means image break. This one means that, okay, you reach the first part of the image, and then you do that for the second line. And once you reach the end of the image, then you're going to have the special token, which is E, which means image end. And this is then how you can support images with different aspect ratios. And then they basically all do this one. So this is not specific to Pixtral. This is more like specific to vLLMs. But yes, they transform everything into tokens. Then they flatten everything. So they have a nice sequence. And how does it work after that? Well, as an input, you have your text that is transformed into tokens, through the transformer that you have. Then you have the vision transformer encoder that I just mentioned, which is also transforming your images into tokens. And then you combine those directly in the multimodal transformer decoder that you have at the top. This one understands all those tokens, and then it can really play around and understand, okay, I have this text, I have this image, everything is token to it, but then it understands those, then combines, and then as an output, it will give you text. And this is then how you can support different aspect ratios, different images, and this is basically everything you have for like multimodal vLLMs. Gonna drink some tea again. And then I'm using vLLM. vLLM, the reason why I'm using it, very fast, easy to use, open source. They actually give a lot back to the community. They are doing some end-to-end inference optimization, which we'll have a look later on. But they also support different hardware, because a lot of people support NVIDIA by default, but they're also different hardware providers. And they support also different range of model support. So this is really nice. Okay, now you have your perfect tech stack. But just because you have the best tech stack in the world doesn't mean that you don't have challenges. So how are you going to solve those? First, you have to look at two things. Those two things, when you deploy, are very, very important. It's the latency against the throughput. Latency is the response time. Usually it's measured in like time to first token, and also the time between each token generation. This is the time between each token generation. Those are the metrics that you're going to have a look at. Very important in real-time systems and interactive applications. Then on the other hand, you have throughput, which is the output of tokens per second. So this is also something very important. Extremely important, if you need to process large amount of data, or you have many users as well at the same time. The problem, those two values are interconnected. So if you reduce the latency, which is good actually, you can have an increased throughput, but not everything is always beautiful, so you have to check on how you can mix those. Also, the higher throughput will allow you to have a higher batch size. And what is batch size actually? This is the number of requests or inputs that your model can process at once. And it's going to affect speed, memory usage, and throughput. And you have two different strategies. You have the third one that is like getting into popular, but there would be a whole talk. So the first one is very naive. Individual requests, one by one, they come, you treat them, but then this doesn't scale. You will, like, if you're ChatGPT and you treat them one by one, you're never going to have an answer. And so what we do is dynamic batching, where we either wait for a certain amount of time, or then once the batch is complete, then we send all those to the LLM, so then we can get the response back to our users. So those are like different strategies. And the batch size is very important, actually, once you're going to deploy your LLM and your vLLM in production. Okay, now you have an idea of those, but you still have to fit your model on the GPU. Quick napkin math, if you want to know if you can fit it, it's actually going to be the number of parameters in billion times the size of the data in bytes. So Llama 3, 8 billion, for example, on FP16, it's going to take 16 gigabytes of RAM, approximately. Pixtral, the one I'm running, an FP16 is going to use 24 gigabytes of RAM. Llama 4 Behemoth, which is 288 billion parameters, in FP16 is going to be 576 gigabytes of RAM. Of course, we optimize them, we're going to quantize them, but that's still a lot of RAM, and that is only to load the models. You're still not generating any tokens here, you just loaded the weights, so you have to keep that in mind. Then you have different GPUs. Okay, let's say I'm actually using an A100 for Pixtral, so A100 is 80 gigabytes of RAM, which means when I'm loading my model in FP16, I'm loading 24 gigabytes of weight, and then I have the rest, that I can use to actually generate tokens. But if you want to deploy Llama 4, then you're still going to need multiple GPUs actually to be able to deploy it, because it's so big that even really big GPUs will not be able to make it through. So how do you do that? Two ways. Either you repeat on different devices. Very easy to do. It's literally a copy-paste. You're going to have a better increase. You're going to have a better throughput, sorry. You have no inter-GPU communication, but your batch size would be lower. So what you do, and what usually we do, and what people are doing, is like you're going to split it, and you're going to chunk the model, and you split it across devices. The problem, you have communication overhead, but you can fit much bigger models. And also you have larger batch size, so then you're happy, users are happy. And you can see it now a bit more. On the first part, on the top part, it's like if we copy-paste the model onto different GPUs. The orange part you see at the top is the space for working. This is to generate the tokens. You can see that if you repeat it, then you're not going to have a lot of space for working. But if you divide it, and if you divide the model in two, then you have more space for working, which means you have more space to generate outputs, which means you can have a higher batch size, which means you can have more users. So this is why we're doing it. This is the reason why we have parallelism. But how do you split a model? Two ways again. Pipeline parallelism. Spoiler alert, you don't use that. You can see if we have 4 layers on a model here. We have the first 2 layers that are on the GPU at the bottom part, but the GPU at the top part is still like waiting, because it's waiting until the first 2 layers are done with the computation. Then, once you're done, layer 3 and 4 are coming, and then, that's beautiful. But then you have a lot of idle time, and you don't want that. So what you do is tensor parallelism. This one, you split up the large matrices that are like internal to the models. So like think of like attention mechanism and think of those. Here we have 4 layers again, but we have half the layer 1 and half the layer 1 on the GPU at the bottom and the GPU at the top, and then you compute those at the same time, and then now you have more intercommunication cost, but you're not waiting for anything. So then, in the end, happy people as well. This is a benchmark by vLLM, which is actually showcasing the impact that tensor parallelism has. If you're not parallelizing anything, which is in gray, the available memory is going to be very low. Whereas if you do parallelize it and you split it into 2 GPUs, you can see you have way more resources available for your model, which means you have higher throughput, which means you can generate more tokens, which means your users are happier. And I might skip this one, or I'll go through it very quickly. But yeah, another thing, why you want to optimize your model, you want to quantize them to reduce the RAM requirements. So we've seen it for Llama 4, for example, 288 billions goes to like 500 more gigabytes. But if you quantize it, then you're at 288 gigabytes in RAM. What you want to do is you want to accelerate the linear layers. This is the attention mechanism. This is like all those ones where you have a lot of computation. And this is in pink here, and this is the idle time on the y-axis. This is the time, on the y-axis, so you can see those are really time-consuming. And it's been shown now that if you quantize it properly and not too hard, also it has a negligible impact on the model quality. I will not go into details, but you have two ways of quantization. What you want to do is you want to do weight plus activation quantization on the right, where you're going to quantize your weights and the activation mechanisms as well. That way you reduce the data movement on your GPU, and you have also more tensor core that you can use. And finally, for the optimization, before my voice is completely gone, you have KV cache, which is what is actually making all the magic to generate the tokens. This is rectangular shape usually, and it's like on the x-axis, it's the maximum sequence length. So for Llama 4, this is 10 billion. But the problem with the default one is that you have a lot of space that is wasted because like all of the 80% of the users, are not using all the input tokens that is available. So then you're only going to have a lot of space available for those 20%, but that means then you can't have a higher batch size, and then you're going to struggle. So what you do KV cache with page attention. This is very similar to what operating systems are doing with memory, where they split the memory into small chunks. Same for LLMs. This is actually, that was invented by vLLM, and this is open source. So if you use them, by default, you have that available. And then the attention mechanism now are split into smaller parts, which means you're not wasting a lot of resources, which means users are happier. And those were like the different parts, for inference optimization, for different things. And now we'll go into demo time. The Wi-Fi was quite spotty, but now I have an internet connection, so it should be good. This is actually the video I wanted to show you. This is a backpropagation explanation. I'm sure most of you are familiar with the YouTube channel. And imagine I missed this class, and this is, well, that would be an amazing teacher, but this is the teacher we have, and we missed it. So I have then my Streamlit UI here. Just because I'm cheating, I'm going to load the index already, because if I have to process those, it's going to take a couple of minutes, and I don't really have time. But what I can show you is, actually, I can show you the data that I have. Well, you should, I'm going to zoom in a bit. For the text, you can see I have this data, and then if I click and I view it, you can see I have the embedding models, which we don't understand, because those are just floats. But then I've added actually a lot of metadata. So the file name, the file type, the file size, a lot of those things that I've mentioned before. Because if I have something actually at scale, then I could filter through that. Okay, enough yapping. Let me check if it's working. My index has been loaded, so I can be like, what was the class about? And now it's checking. Sweet. Nice. Well, should be working, but I guess no. That's the demo effect for me. Well, should have been working, but I guess it was not working. OpenAI. Okay, sweet. I'm going to try again. See, this morning in my hotel worked perfectly. I was very happy. I was like, let's go. No, it's not working. Yes, okay. What was that? Maybe not all caps. Maybe all caps, so it knows I'm very angry. Okay, it's not working. Well, that was it for my demo. Thank you.
All right, great presentation. Lots of technical details. Appreciate you hanging out there with your voice. We have a few minutes for questions. Before we go in there, though, a reminder of using the InfoQ app to share your feedback about the presentation. So please do that. If you have questions, raise your hand. We have volunteers to run the mics over. So one over there.
That was one of the person that believes RAG is dead. I'm scared now.
Hello. Thank you for this presentation. I just have a question because I'm using RAG, but there is another concept. It's named CAG. It's like a context retrieval generation. Did you use it? What do you think about it?
So you mean CAG I have to repeat the question as well. So my question, so I have to repeat for the recording. So what do I believe, what do I think, about CAG instead of RAG, which is like context augmented generation?
Exactly.
Which is the one that was...
It's cache augmented generation.
Cache, so not the one from Anthropic then?
No.
Oh, then.
From IBM, actually.
I've seen this one, but I haven't used it at all, so I
Okay.
don't have an opinion on it, sorry.
Question back there.
Hi, thanks for a great talk. I was just wondering, because I saw the error was related to OpenAI.
Yeah.
But are you using OpenAI in
No,
your
it's just
architecture?
it's the SDK. It's the
Okay.
OpenAI SDK, you know, and then vLLM is just supporting it, so that's why I was using it.
Cool, and what was the interface where you were seeing all the data?
This is Trimlet. You mean this? No, this one?
The green one, yeah.
Sorry.
Exactly.
This one is called A2, but it's only an interface if you use Milvus, the vector database. It just allows you to talk to it and see it. Other questions?
This one up here.
Thank you for the
Yeah, sorry.
speech. RAG have multiple components, and one of them is chunking. What is the best strategy of chunking, especially when you're dealing with variety of documents?
So that's a very good question. There's not a good strategy. There's not one good strategy for chunking. Same for indexing. Everything is a trade-off. I would say, depending on the data now, like if you have really long PDF, it's actually good. One-page PDF chunking, and then you add some context about the chunks, though, is really, really good. So say Anthropic, this is what I thought he was talking about, is contextual augmented generation. So then you add context to your chunks, being like, this is about, you know, DoorDash IPOing, or this is about, you know, those things, and then it will have a better idea. But there's not really one rule for chunking, unfortunately, yet.
So there is a limitation, depends on the variety of document that we can and we can't use RAG.
No, there's like, it's just going to depend on the chunking strategy you have in your document. So if you have PDFs with very complex images and data there, maybe have a look at CallPally and like different ways, which are going to take screenshots of the PDF, and then they transform those into tokens that we've seen, and then you search through that. So that's very good if you have complex PDFs. If you have Excel files, it's going to be very different. So it just depends on your data, unfortunately.
Thank you.
You're welcome.